After deriving general heat conduction equation in Cartesian, cylindrical and spherical coordinates, now let us talk about the specific applications of all these equations. So let us start first with one-dimensional steady-state heat conduction without heat generation through homogeneous and isotropic material. And during this entire discussion, I am going to consider constant thermal conductivity K, and it is constant with respect to temperature. First, let us analyze the above mentioned condition for a geometry plane wall. We are going to discuss the above mentioned conditions for different geometries like plane wall or slab, composite wall, plane cylinder, composite cylinder, plane sphere and composite sphere. So let us start our discussion first with plane wall. It is also called as slab. That is one-dimensional steady-state heat conduction without heat generation through homogeneous and isotropic material of plane wall oblique slab. For this, let us consider a one-dimensional steady-state heat conduction through a plane wall made up of homogeneous and isotropic material having thermal conductivity small k and constant area normal to heat flow is A. Also, there is no heat generation within this slab while heat is being conducted. So we have to find out the purpose of this entire analysis. We have got twofold purpose, or we have got two aims of this analysis. First, I want to discuss temperature variation within the slab, and second, to calculate heat transfer rate. In order to uh, in order to achieve these two ends, let us consider a single or plain wall or slab. It is made up of homogeneous and isotropic material having its thermal conductivity K. Its thickness is, let's say, L. This thickness is also called as length of path of heat flow. And area normal to heat flow is A. This area is the area of the wall normal to heat flow. Let's say this represents distance x equal to 0, and this distance represents x equal to L. Let's say temperature of left face of the wall is maintained at T1, and temperature of the right face of the wall is maintained at T2, such that T1 is greater than T2. Now, by virtue of this temperature difference, Q, we are considering heat transfer only in the x direction. We are not considering any heat transfer in the y direction. So there is no heat transfer in this direction. So no heat transfer either in y direction or in z direction. That means I can assume the other lateral faces, that is faces in the y direction, are insulated, and this face is also insulated. So as heat transfer takes place from this left face to the right face at the rate of heat transfer Q, the temperature of the wall between left and right face is going to change. And let's say temperature at any distance x is Tx. So the purpose of this analysis is to calculate this Tx and to calculate this heat transfer rate. Also, let us draw the equivalent electrical circuit of this heat transfer phenomena through a plane wall. We know heat transfer phenomena is having analogy with electrical energy transfer. So we can represent its equivalent electrical circuit. To draw that, This will be the equivalent electrical circuit of the heat transfer to this plane slab, where flow quantity is represented by heat transfer rate. The potential difference is nothing but temperature difference. So there must exist a thermal resistance offered by the wall of the material, and this we want to calculate. So this is the equivalent electrical circuit of the heat transfer through this plane slab. So let me give title to this diagram. So these two diagrams represents heat conduction through plane wall. Now, how to achieve these two aims? That is, find out the temperature variation within the slab in the x direction and to calculate heat transfer rate. For that, we need to recall generalized heat conduction equation. So we have three types of general heat conduction equation. So which one we must recall? Think over this for 5 seconds. Yes, I have to recall general heat conduction equation in Cartesian coordinates, because here the shape of the body through which heat is being conducted is of rectangular shape. So recalling general heat conduction equation in Cartesian coordinates. Do you remember that equation? So let me write del square T over del x square, del square T over del y square plus del square T over del z square plus q dot g over k is equal to 1 over alpha del T over delta. And this is the generalized heat conduction equation through for heat transfer through homogeneous and isotropic material. But this equation is not applicable to our case. We have to modify this equation according to the stipulations. So what are those stipulations in our case? The first stipulation is that we are considering one-dimensional heat transfer or one-dimensional heat conduction. And particularly in the x direction. What does it mean? I am not considering heat transfer and temperature variation due to it in y direction. Similarly, I am not considering any heat transfer and temperature variation due to it in the z direction. So these two terms will become zero. Second stipulation in this case is considering steady state heat conduction. That means for steady state, variation of temperature with respect to time will be 0. Third condition, I am not considering any heat generation within the slab wall while heat is being conducted. So this Q dot G will also become 0. So applying all these three stipulations to equation, generalized heat conduction equation, so it will become to generalized heat conduction equation. It becomes, for our case, that is one-dimensional steady state heat conduction, it becomes del square T over del x square is equal to 0. Or in the limiting case, it will become d square T over dx square is equal to 0. So let's say this is equation number 1. Now what is the utility of this equation d square T over dx square is equal to 0? So utility of this differential equation is that if you solve this equation, you will get one expression for T, and that T will give you variation of temperature with respect to X in the slab. What is that X actually? This is the X. That means if I want to calculate, let's say, heat transfer at this distance, I can calculate at this distance, at this distance. So that is given by the solution of this differential equation d square T over dx square is equal to 0. Now, how to get solution of this equation? So mathematics has answer for this question. To solve this equation, to get the expression of T in terms of x, we have to integrate it twice. Why? Because it is a second order differential equation. So let us integrate. So first integration, after first integration, what I will get? If I integrate this, d square T over dx square is equal to integration of 0. What I will get? I will get dt over dx is equal to some constant C1. Now, if I integrate it second time, that is integration of dt over dx is equal to integration of C1. Sorry, let us modify this equation before integrate it. So dt is equal to C1 dx. Now let us integrate this. Integration of dt is equal to integration of C1 dx. If you integrate this, what you will get? T is equal to C1x plus C2. So solution of the differential equation d square T gave me this expression for T is equal to C1x plus C2. Let's say this is equation number 2. So if in this equation, if I put the value of x from 0 to L, it will give me temperature of the slab at that distance. So this is the importance of the equation number 2. Okay. Now, but what is the problem with the equation number 2? I can put any value of x between 0 to L, but in order to get the value of this temperature at that distance x, I don't know the value of C1 and C2. And what are C1 and C2? C1 and C2 are nothing but constants of integration. And I don't know their value. So I must be able to express the values of C1 and C2 in terms of known values. Now, what are the known values in this analysis to us? Let us refer the diagram. In this diagram, this thickness of the slab is known to me, that is x equal to, that is L. I know the value of the temperature at left face, that is distance x equal to 0. And I know the value of this temperature at the right face at distance x equal to L. So these are the known values of temperatures and thickness of the slab. So if I could express the values of C1 and C2 in terms of either two temperatures T1, T2 and L, then I can easily calculate the temperature. So to get the value of this C1 and C2, I must have two boundary conditions. So I have to recall the boundary conditions. So what are those boundary conditions? Boundary conditions means, in a simple sense, the known values of parameters related to heat transfer. So the very first boundary condition I have, at left face, I know the temperature, that is at x equal to 0, T is equal to T1. And what is second boundary condition? At right face, that is x equal to L, T is equal to T2. So these are the two boundary conditions I have. Now let us put these two boundary conditions into equation 2 one by one to get the value of C1 and C2. So boundary condition, let us solve first equation number 2 and boundary condition 1. What it will give me? At x equal to 0, T is equal to T1. So T will become T1 at x equal to 0. So this will give me the value of constant C2 equal to C1. And if I solve the equation 2 and boundary condition 2, it will give me at x equal to L, T is equal to T2, C1, x will become L plus C2. Now I know the value of constant C2, that is T1. So value of constant C1 I can get as T2 minus T1 over L. Now let us put the values of these two constants into equation 1. Putting the values of constant C1 and C2 into equation 2. What I will get? T is equal to, the value of C1 is T2 minus T1 into X over L plus T1. So this way I can get the value of so I got this expression. T is equal to T2 minus T1 into X over L plus T1. Let's say this is equation number 3. So the equation number 3 will give me the variation of temperature in the slab at the distance x. I can put any value of x equal to 0, x equal to L, x equal to half, x equal to 0.25 L, anything. Now let us check whether this equation is correct or not. In this equation, if I put x equal to 0, what I will get? T is equal to T1. And we know this value is known to me. If I put x equal to L, what I will get? T is equal to T2. Simply, if I put x equal to 0, T is equal to T1. And if I put x equal to L, L will get cancelled, T1 will get cancelled, and T will equal to T2. That means this equation is the correct equation. So our first aim is achieved by analyzing the heat one-dimensional steady-state heat conduction through this plane wall or slab. I can get the expression of T to calculate temperature variation across the slab due to heat transfer. Now, if I write this expression, I can write this expression in the non-dimensional form. Non-dimensional form will give me T minus T1 over T2 minus T1 is equal to x over n. Now, do you remember if I plot the T minus T1 over T2 minus T1 with reference to x, what geometry I will get? This is nothing but equation of line. Now, what is the conclusion I am going to draw from this equation? This is a mathematics, but what I am going to draw? This equation represents that, let's say this is equation number 4. So equation 4, from equation 4, temperature distribution or variation within the plane wall is linear. So the temperature variation is linear. Now what does it mean? That is, whatever temperature is going to vary of the plane wall between x equal to 0 and x equal to L by virtue of this heat transfer by conduction is linear. So I can represent this temperature variant with the help of a line, and this is nothing but temperature variation. So this is called as temperature profile. And it is linear in shape. So that is the expression T minus T1 over T2 minus T1 is equal to x by L can be plotted on x axis and t axis, and its shape will be linear. That is temperature profile of the slab plane wall or slab is linear. Many times this question is being asked in gate examination for 1 marks. What is the shape of the temperature profile while heat is being conducted in a plane wall? Now our first aim is achieved. Now let us find out the expression for heat transfer rate. That is Q. Now how to calculate this heat transfer rate, which is taking place across the plane wall by virtue of temperature difference T1 and T2. Now here, once again, we are considering heat transfer only in one direction, that is one dimensional heat transfer. So in order to calculate this heat transfer rate, now I can easily apply Fourier's law of heat conduction. So from Fourier's law of heat conduction, Q is equal to minus K A dt over dx. where T is the temperature variation in the direction of heat flow and dx is the thickness of the material in the direction of heat flow, which we have taken L in this case. And what will be the T? I want to simplify this Fourier's law of heat conduction for this plane wall. So I can put the expression of this T from equation number 3. T2 minus T1 into x over L plus T1 and value of dx as L. So let us simplify this Fourier's law of heat conduction. In our case, Q is equal to minus K A d over dx. What is the expression I have got? T2 minus T1 into x over L plus T1. So if I simplify this, what I will get? Minus Ka. If I differentiate this, T2 minus T1 is the difference. It is constant. L is also constant. And differentiation of x will give me 1 plus 0. Or minus Ka T2 minus T1 over L. If I take this side into consideration, the equation will become Ka T1 minus T2 over N. So this is the rate of heat transfer which is taking place across this plane slab of thermal conductivity K, area normal to heat flow is A, thickness L, and temperature difference T1, T2 in watt or joule per second. So this way our second aim is also achieved. So please keep this thing in mind. If heat is being conducted into a plane wall or slab, the temperature profile is linear, its shape is linear, and the rate of heat transfer is given by Q is equal to K T1 minus T2 over L watt. Now let us modify once again this equation to get very important parameter. Now let us modify this expression in the form of Q is equal to del T over RTH. Do you remember this? It is coming from electrical analogy of heat transfer. This equation we get from electrical analogy of heat transfer. So if I compare the equation number 5 and equation number 6, what I will get? I will get very important parameter related with the plane wall. Okay, so Q is equal to T1 minus T2. I am modifying the equation number 5. Sorry, 5 and 6. L over KA. So if I compare, let's say, equation number 6 and this equation, what I will get? The expression of RTH wall is equal to L over KA. And it is nothing but thermal resistance of the plane wall. This is again very important parameter. We are going to use it frequently while solving the numerical problems. And this formula is given in data book. No need to mug up this formula. I will tell you where this formula is given and how to use this formula. So from the analysis, from the one-dimensional steady state heat conduction without heat generation through homogeneous and isotropic material of plane wall or slab, we got three important equations. Three, rather four. The first one, equation number 3, it will give me temperature variation across the slab or plane wall at distance of x. The second expression I got in the form of non-dimensional form, and it tells me the temperature profile inside the plane wall or slab is linear. Then I could calculate, or I could get the expression of heat transfer rate which is taking place of plane wall or slab by virtue of the temperature difference T1 minus T2, made up of material having thermal conductivity K, area normal to heat transfer A, and thickness L. And the final expression I could get is how much the thermal resistance will be offered by the wall to the path of the heat flow is L over Ka. And its unit is degrees Celsius per watt or Kelvin per watt.